All right, we got one more example of a type of force that's acting on an object here. So this is called hydrostatic force. So hydro meaning water. So this is basically the force that water is putting on an object submerged in water or sort of on the edge of water. I think the best way to kind of think about, like we've got this vertical plate here that's sitting underneath water, is to view it as maybe this is like a window on the side of a pool or like an aquarium. Like if you're at like a big aquarium where you're looking at fish and they've got, windows and things that this is essentially submerged in water and there's force pushing against it from that water. And so the question is how much force is pushing on this plate that's submerged in water? So what we're going to need to do is put this on an axis somehow. So the easiest thing to do, since this is a semicircle, is to put it on an axis so that its center is sitting right there at 0, 0, and that the radius is sitting out here at 5. And then in terms of, the depth of this, so the top of our water is up here at the top of our picture. So again, that's 5, and this is 2 feet below the top. So the total depth, like the deepest this window goes, is 7 feet. And then what do we need to do? So now we need to kind of figure out what's happening with this. Like, so what is pushing on this? So what is our force here? Well, we've got the density of water that's pushing on it and the area of this window and then the depth that we're at. And so if we think about things that are changing on this, the density of water, that's the same no matter what, but the area of this, like it's bigger down here than it is up here. I'm gonna take those lines off. So the area of it's kind of different depending on where we are, and so is the depth. Like it's, of course, right here, we're not as deep as we are down here when we're all the way 7 feet underneath the side of the pool or whatever it is that we're looking at. So the area that we're looking at and the depth that we're at changes based on sort of where we are on this circle. So, here we are. What do? We make slices. So let's take a look at a slice of this and think about what's happening here. So the way that I set this up, and you could set this up so that this is turned and, that's the x-axis and maybe this is the y-axis, but just, for how my brain is looking at this, I'm going to have this be the x-axis and that be the y-axis. So when I'm making my slices here, I'm going to get delta y. So that's part of the area of my slice. That's part of the area. And we also need to figure out our area, what is actually this length, but actually what this whole length is, because we're making little rectangles here. And so we need all the way across there. Well, this is a half circle. So this function right here, the function of the window, we'll call this a window, is that it's a semicircle. It's the top half of a circle with radius 0, oh, radius 5, excuse me, and it's centered at 0, 0. So because we're going to have delta y right here, and that's going to be our variable, that's why that's kind of one of the nice, sort of first nice things you want to do, just like we were looking at with volume. Let's take this equation and solve it for x. So we get x squared is equal to 25 minus y squared, and then x is equal to the positive square root of 25 minus y squared. And again, that's just kind of grabbing this part of our circle for us, that's all we need right now, because we just want to go, from this axis out to the side here. So the area of our strip, area of the strip of window that we have here, it's going to be, so this length right here, that is 1 of our square roots of 25 minus y squared. So if we need 2 of those, because we need to go all the way across that strip, we need to get a second one here. That's going to be 2 times that value. and that's going to give us all the way across. So that 2 comes because we have to double that length. And then times delta y. So that's the area of our strip. Let's see, what else might we know? Maybe you know this, maybe you don't. We usually give these in the problem set statement, but the density of water, that is a constant, and this is in our standard US measurements because that's what this problem is in. It's 1,000 when we're in metric. It's 62.5 pounds per cubic feet. Cool. All right. So then that gives us this part. So we kind of, if we look at on our, up here, we've got depth, we've got density, or we've got area, we've got density. We need depth still. We need to figure out like how deep is this strip in this water. All right. So let's think about the depth. So I'm going to do a little bit of erasing over here, just erasing this little bit right here. Whoa, too far, too far. Okay, so we need to look at how deep this is in this water. I think we need a bright color here. So it's this deep, but it's also this deep. So it's that depth right there. We've got to figure that out. Okay, well, let's think about what we know here. This amount right here is going to be our y sub I. And the whole way, right, from the top of the surface of the water down to the bottom, that's 7 altogether. And what we need is this red amount right here. Well, this is going to be that whole depth 7 minus this little bit right here, that y sub I. So our depth, let's go back to the right color here, that's going to be 7 minus y sub I star. So the force pushing against this, the force on one strip of this is going to be the sum. Well, we won't do the sum yet. We'll just do the force on one. It's going to be the density of water times our area times our depth. And this actually right here is also y sub I star being squared. So what do? This is the force on one strip. We would add these up and we would get 62.5 times 2 times 7 minus y, and then our square root of 25 minus, get all of our notations on there, and then delta y. We always put delta y at the end. And boy, what does this look like? Maybe it'll help if we do the limit as we go to infinity. This is just another integral. That's integrals after integrals after integrals. And this is going from 0 to 5. So again, looking at what we did down here, or back up here on our picture, we started here at 0. That's the deepest it is. And then going up until 5, and that's the least deep it is, the shallowest it is. So it's going from 0 to 5. And then we have, what is that, 125, 7 minus y, all our y sub I stars turn into regular y's. 25 minus y squared dy, and I spent about a minute looking at this going, I don't want to do this, so I went to our good friend Wolfram Alpha and said, hey, will you find this integral for me? And it did. And you get 11,972 pounds of force here, or 1.2 times 10 to the fourth. And we're in pounds.